A black hole hurtling toward Earth, its immense gravitational pull threatening to consume our planet and end humanity as we know it. In this thought experiment, we're not content to sit idly by and await our fate. Instead, we embark on a daring quest to destroy this cosmic predator using every tool at our disposal, from conventional weapons to cutting-edge theoretical concepts. But before diving into the strategies, it's essential to understand what we're up against. Black holes aren't just voids in space. They're regions where gravity is so intense that nothing, not even light, can escape once it crosses a boundary known as the event horizon. Black holes form in a couple of primary ways. Supermassive ones, often lurking at the centers of galaxies like our Milky Way, emerge from the collapse of vast gas clouds and can weigh in at thousands to billions of times the mass of our Sun. Stellar mass black holes, on the other hand, are born from the dramatic deaths of massive stars. When such a star exhausts its fuel, it undergoes a supernova explosion, and if the core is dense enough, typically a few solar masses, it collapses into a black hole. Our galaxy alone is estimated to host around 100 million of these enigmatic objects, most of them quietly spinning through space without posing an immediate threat. What makes black holes so formidable? Their defining feature is extreme density. All that mass is crammed into an infinitesimally small point called a singularity, surrounded by the event horizon, which acts like a one-way membrane. Approach too closely and you'd experience spaghettification, a gruesome process where tidal forces stretch your body lengthwise while compressing it radially, turning you into a stream of atoms long before reaching the center. Black holes also possess angular momentum, meaning they rotate, and they can carry an electric charge. These properties must remain balanced with their mass for the black hole to maintain stability, much like how a spinning top needs the right speed to stay upright. Now, with this knowledge in hand, let's consider our first defensive strategy: unleashing humanity's most powerful weapons. Suppose we gather every nuclear warhead on Earth, thousands of them, and launch them directly at the oncoming black hole. The combined energy release would be staggering, equivalent to hundreds of thousands of times the destructive power unleashed during World War II. Nuclear explosions are devastating on planetary scales, vaporizing matter and releasing immense radiation. Surely, this barrage would shatter the black hole, right? Unfortunately, physics has other plans. Black holes don't explode from added energy. They thrive on it. As the nukes approach, their matter and energy would simply be absorbed, crossing the event horizon and adding to the black hole's mass. Rather than destroying it, we'd be feeding it, making it larger and more massive. This counterintuitive outcome stems from the fundamental nature of black holes. They consume everything in their path, converting it into additional gravitational strength. The famous phrase, "What doesn't kill you makes you stronger," applies here. Except for black holes, nothing really kills them in this manner. Undeterred, we might escalate to other conventional armaments. What about high-powered lasers, particle beams, or even hypothetical superweapons capable of delivering focused energy blasts. Lasers, for instance, could theoretically deliver precise, intense beams, but light itself can't escape a black hole. Any beam directed at it would bend and spiral inward due to gravitational lensing, ultimately getting sucked in. Bullets or projectiles fare no better. Their kinetic energy becomes part of the black hole's accretion disk, a swirling ring of superheated matter that only enhances its growth. Even more advanced kinetic approaches, like accelerating asteroids or spacecraft at relativistic speeds toward the black hole, would fail similarly. The impact would release tremendous energy, but all of it would be incorporated into the black hole's mass, per Einstein's E equals mc squared. In essence, any attempt to bomb a black hole turns into an inadvertent buffet, increasing its size and gravitational influence. This realization forces us to abandon brute force and pivot to smarter, more nuanced tactics. As the black hole draws nearer, humanity's survival hinges on innovation. We've established that direct assaults with matter or energy only empower the enemy. So, what if we turn to exotic physics? Could we engineer countermeasures using principles from quantum mechanics or general relativity? In the next phase of our analysis, we'll explore ideas like crafting artificial black holes from antimatter, or harnessing hypothetical counterparts like white holes. But first, reflect on the basics. Knowing your adversary is key, as ancient strategists like Sun Tzu emphasized. With black holes, that knowledge reveals their invulnerability to simple attacks, pushing us toward the realms of theory and speculation. Having exhausted conventional weaponry in our hypothetical battle against an encroaching black hole, we must now venture into the realm of advanced physics and speculative science. The core challenge remains. Black holes absorb rather than repel, turning any influx of matter or energy into fuel for their expansion. To counter this, our next strategies involve harnessing exotic materials and phenomena that might exploit weaknesses in a black hole's structure or behavior. Let's start with antimatter, the mirror image of ordinary matter, where particles have opposite charges and properties. Antimatter isn't science fiction. It's produced in small quantities in particle accelerators like those at CERN. To create it, protons are accelerated to near-light speeds and smashed into targets such as iridium, yielding antiprotons that can be captured and combined into antimatter atoms. In our scenario, we'd scale this up dramatically, perhaps deploying orbital facilities to generate enough antimatter to form a miniature black hole. The idea? Collide this antimatter black hole with the incoming one, hoping for a cataclysmic reaction. When matter and antimatter meet, they annihilate, converting entirely into energy per Einstein's equation. A black hole made of antimatter would behave gravitationally like one of regular matter. But the collision could trigger a massive energy release. However, reality intervenes. As the two black holes merge, their event horizons would combine, and any annihilation energy would be trapped inside, simply adding to the total mass. The result? A single, larger black hole, now even more threatening as it barrels toward Earth. This approach backfires spectacularly, underscoring that gravity dominates over particle interactions at these scales. Frustrated but persistent, we turn to the conceptual opposite of a black hole, a white hole. In theoretical physics, white holes are predicted by the mathematics of general relativity as time-reversed black holes, where black holes pull everything in. White holes expel matter and energy, allowing nothing to enter. They might emerge from wormholes or quantum effects, though none have been observed. The strategy here is to somehow acquire or create a white hole and hurl it at our adversary, pitting yin against yang in a cosmic showdown. Upon impact, the interaction could be explosive. The black hole's insatiable hunger clashes with the white hole's repulsive nature, potentially leading to mutual destabilization. Energy bursts, including intense gamma rays, might erupt, capable of sterilizing nearby space with radiation doses far exceeding lethal levels. Think instant cellular destruction rather than gradual illness. Yet, problems abound. White holes are purely hypothetical. We lack the means to produce one. Even if we could, the merger might not annihilate both, but instead form a complex, unstable structure. Or worse, release uncontrolled energy that endangers us as much as the black hole. Pushing further into speculation, what about time travel? Building a time machine might allow us to intervene before the black hole forms or alters its path. One theoretical avenue involves wormholes, tunnels through space-time, connecting distant points or times. By stabilizing a wormhole with exotic matter, which has negative energy density to prevent collapse, we could link the present black hole to its past self. Traveling backward, we'd force the black hole to regurgitate absorbed mass, effectively turning it into a white hole temporarily. If we journey far enough, we might reach the progenitor star or gas cloud and disrupt its collapse, perhaps with precisely timed energy injections to prevent singularity formation. This echoes concepts from physicists like Kip Thorne, who explored traversable wormholes. However, wormholes require negative energy, which we've never harnessed, and time travel risks paradoxes, like altering history in ways that prevent our own existence. Moreover, without proven technology, this remains a tantalizing but impractical dream. Another angle: superluminal explosions. Since light can't escape a black hole, we'd need a bomb detonating faster than light to overcome the escape velocity at the event horizon. Tachyons, hypothetical particles that always travel faster than light, could theoretically power such a device, blasting the black hole from within. But relativity forbids anything with mass exceeding light speed, and tachyons are unconfirmed. Attempting this might violate causality or create instabilities, but without the tech, it's moot. These exotic tactics highlight the ingenuity required to challenge a black hole. Yet each reveals fundamental limitations in our understanding and capabilities. Antimatter feeds the beast, White holes elude creation. Time machines flirt with impossibility. And faster-than-light ideas defy physics. As the black hole looms larger, we must consider deforming its very essence, targeting density, horizons, or equilibrium parameters. In the final part, we'll delve into these deformation strategies and ponder natural dissolution processes, weighing whether destruction is feasible or if evasion is our only hope. As the black hole surges ever closer, its shadowy maw widening like a predator's jaws, ready to snap shut on humanity's fragile existence, our options dwindle to the brink of desperation. We've thrown nukes, antimatter, and even the fabric of time itself at this unrelenting force, only to watch it grow stronger, mocking our efforts with its silent, insatiable hunger. Now, in this final stand, we target the black hole's very core, its structure, its boundaries, its delicate balance. Deformation isn't just a strategy. It's a high-stakes gamble that could unravel the beast or doom the universe in a cataclysm of our own making. First, consider assaulting the heart of the monster, its singularity, that point of infinite density where physics breaks down. If we could somehow stretch or dilute this ultra-compressed core, stripping away its density, the black hole might cease to be. But how? Black holes aren't solid objects. They're warps in space-time itself. Science debates whether singularities are finite and malleable or eternal voids beyond comprehension. Venturing inside to stretch it, forget it. That's a one-way ticket to spaghettification. Your body elongated into cosmic noodles amid crushing forces that defy imagination. One wrong move, and you're not just destroyed. You're erased from reality, atom by tortured atom. Yet hope flickers in the shadows. What if we pierced the event horizon, that impenetrable veil sealing the black hole's secrets? Imagine engineering a probe or exotic particle beam to puncture this boundary, creating a leak from which mass and energy could hemorrhage out. Without its horizon, the black hole loses its grip. No more inescapable trap, just a fading echo of gravitational might. The mass drains away like blood from a fatal wound, shrinking the entity until it's nothing but a whisper in the void. But beware, tampering with the horizon risks unleashing horrors beyond control. Quantum effects could trigger a runaway cascade, birthing instabilities that ripple through space-time, potentially fracturing reality itself. Is this victory, or the spark that ignites universal Armageddon? Escalating the peril, let's manipulate the black hole's vital signs, its spin and charge, those precarious parameters keeping it alive like a heartbeat in overdrive. Picture this. We bombard it with charged particles, amping up its electric field to extremes, or accelerate its rotation with precisely timed infusions of angular momentum. Push too far, and equilibrium shatters. An overcharged or overspun black hole might expose a naked singularity, a raw wound in the cosmos, where predictability crumbles. Laws of physics could warp unpredictably. Time loops, infinite energies, dimensions unraveling. We aim to kill the black hole, but in our frenzy, we might birth a monster far worse, one that devours not just matter, but the very rules governing existence. The thrill of success teeters on the razor's edge of total annihilation. Alternatively, we could bleed it dry from the outside. By dangling objects near the event horizon and extracting rotational energy via the Penrose process, flinging parts away while others fall in, we slow its spin to a crawl, even halting it entirely. The black hole weakens, its accretion slowed, but it doesn't vanish. It's like chaining a beast rather than slaying it. The threat lingers, ever present, waiting for a slip-up. In the grip of this cosmic thriller, one last agonizing truth emerges. Black holes can self-destruct, but only through the agonizing crawl of eternity. Enter Hawking radiation, that quantum whisper where virtual particle pairs flicker into existence near the horizon. One tumbles in, the other flees, siphoning a minuscule sliver of mass each time. Over eons, trillions upon trillions of years, this erosion whittles the black hole down to nothing, exploding in a final burst of gamma rays. Patience becomes our weapon, but with the devourer closing in, do we have time? Ignoring it won't save us now. It dooms generations to a vigil in the stars, fleeing until the universe itself grows cold. So, can we destroy a black hole? The verdict is a heart-pounding no, not with our current arsenal, and perhaps not ever. These titans of the cosmos are woven into the fabric of reality, defying our boldest assaults with effortless supremacy. Yet in this what-if saga, the real triumph lies in evasion. Rocket humanity to the stars, outrun the shadow, and live to ponder greater mysteries. If a black hole ever truly targeted Earth, improbable as a lightning strike on a whisper, our ingenuity might just spark survival. But for now, gaze at the night sky and wonder, what other voids lurk, waiting to test our resolve?